Hello, everybody. This is Professor Ma, and this is the section on fluid pressures, not water, hydraulic pressures, if you like. Okay, the scenario is this. Suppose we have a flat plate submerged in water. Okay, let's say, okay, and then there's water pressures, and in particular, how do we measure the force it's exerted on the plate? And suppose A is the area of the plate and H is the depth it's in. So the rho is the density of the fluids, and uh, we have something like that. Then the force on the plate is going to be the water it carries on top of it. Okay, and that's going to be density times the volume. In particular, this part area times height is the volumes of the cubicle or the cube of, and then you multiply whatever that the density of that fluid is, water. Okay, let's see. Okay, notice when we say that these pressures in downward directions is actually pressures in all directions. In particular, think of these manners. I mean, stretch your thinking a little bit. Instead of just a plate, what we have is a pizza box. Okay, inside it's you have machines. You can measure the pressure. Then you will have pressure from bottoms exerting on the bottom plate and the pressure on the side plates. So we're not just but we are concentrating on, say, suppose the pressure from downward. Okay, and in particular, suppose we have a plate submerged vertically, we can measure the pressures on the plate. Okay, of course, the deeper part of the plate has more pressures against it because deeper. And we're going to calculate and put that into formula. Okay, again, we're going to sum over all the pressures, if you like. Okay, and we're going to calculate the pressure along each individual strips. And what strips? We're going to, again, partitions the coordinate axis. Over here, I set x equal to 0 to be the top of the plate, and specify how far the plate is submerged. Well, just like before, there's no reason why we couldn't set x to be stuff from here. X is x equal to 0 from here. Then the plates submerge from H to whatever. Okay. So, or we can do it from bottoms up. Okay, and so the flexibility is okay. We can set our x to be 0 here, and then this will be b up to the top of the plate, and on top of it, and then keep going. There's still h to the surface. So the choice of the axis depends on the shape. It leads you to slightly different calculations, sometimes quite different. And so sometimes actually think of the choice of the directions is something sometime more cause calculation problems, sometimes make things easier. Okay. So anyway, again, this is a cross-sectional problem. So what we do is, okay, suppose here's a setup and I know the cross-sectional length, Lx, okay? So Lx times dx is out of skinny strips. And I want to calculate the pressure on these strips. So think I will have a very thin, like streamers. You put it down in water, you want to measure the pressures on that little very thin strips of area. Okay. Now, at that depth, basically, it's the same as the. We can assume that at that point the pressures is going to be approximately the area. Okay. Of the strip times the height In this case, the height will be x plus h, the way this one set up. Times density, times the density. So I imagine these little strips, basically vertical, horizontal, the same pressures. Okay, so if it's horizontal, then I have this formula, the area times the height times the density of the fluids. Okay. And it's written in this manner. Okay. And we want to make thinner and thinner strips, let delta x go to 0. So this sum over all the pressure of all the strips turns it into an integral. Okay. And over here, Lx times dx. I'm going to point out again this Lx dx. This is the d area. Okay, that's the basically how much the area is. Okay, times the distance, which is the distance to the top. Okay, x plus h. In general, depends on how you set x-axis, and this is the formula for the force on the plate, on the area submerged vertically. Okay, this xa to b is really, again, it depends on you put the x-axis pointing up, pointing down, starting from the bottom, or wherever it's convenient. Okay, so here is a questions. They find the force on the square sitting inside the fluid. Then the cross section. Remember, we need to find the cross sections length and how far this length times dx, the area, how far this area has to travel. And that's the height over the area. Okay, so the length is 5. What's the height to the surface? Well, it's going to be x plus 6. Okay. So the area times the density. Okay. So the have the cross-section area Lx times the distance. This is Lx. This is the distance we travel. Okay. And integrate that. Okay. I leave you to check the arithmetics, okay, algebra. I mean, and here is a different way of approaching it, setting the x differently from top down. So I'll let you coincide with the pictures of the setting for the scale, and you get the same answers. And then what kind of things we're going to submerge? Well, the things we can extract cross sections, like what? Like some kind of regular triangular shapes. So in this case, if it's a triangle submerged, then the cross sectional lengths are obtained by similar triangles. Okay. So again, so you have the similar triangle, you have these ratio relationships. You can solve for the cross-sectional length. Once you have the cross-sectional length, then from the picture of the setups, you have these answers. Then how far is it at this stage to the top? That's the distance functions. Okay, and then this is the calculations. And the other shape we're going to do is cross-sectional length that's easy to extract. Again, these are all horizontal cross-sectional lengths. These are circles. Okay, so these we use Pythagorean theorem. Okay, so I'll leave this up to you to read and set up integrals. And this one requires substitution to finish the problem. Okay, so yes, and this is all these things we did from area up to this point, volumes, works, and fluid pressures, and volume of spinning stuff require cross-sectional things. So yeah, we will talk about that, review that later. Okay, bye-bye. Okay, bye-bye.